Hello everyone, this is Dr. Lennon, and today we're going to go through some examples of applications of systems of equations. So these are essentially word problems that arise, and what they result in is a system of equations after you set them up. So we've already covered how to solve those, whether it be from the substitution method or the elimination method. And so now we're just going to practice setting these things up. So for some of them, a chart might help. For other ones, it's simply choosing how to label the variables. Again, we're going to start off with a really easy one. The sum of two numbers is 90, and the difference of them is 38. Find the two numbers. So if you call one number x and the other number y, we know that x plus y has to add up to 90. And then if you take their difference, x minus y, that would be 38. So very, very quickly you see the system of equations. This is already set up for elimination. You can just add both equations together. X plus x is going to give 2x. Y minus y cancels out, and you end up with 128. And then you just need to divide by 2. So x is equal to 64. So that's one of our numbers. And then we just plug in the 64 to figure out the remaining one. So 64 plus y should be 90. So we just subtract 64. So we end up with y is equal to 26. Those are our two numbers. So very straightforward for the first one. Not really even an application. They're almost just telling you the system of equation in words. But sometimes you see that. And maybe you'll see it even a little more difficult. But for number two, we start to get into ones that are a little bit more interesting, have some applications. Not so much with this one, but I mean, so building A is 190 feet shorter than building B. So I like to go a sentence at a time and try and see if I can write an equation. A lot of students, I think, make the mistake of reading the entire problem. I like to do it one sentence at a time, and if I can write an equation, then I go ahead and write an equation. So if building A is 190 feet shorter than building B, that means if we took A and added 190 feet to it, we would get the same height as building B. So, okay, we got one equation. That's not bad. The total height of the two buildings is 1,510 feet. That means A plus B is 1,510. So this one is set up pretty well for substitution. What I would do is I would just substitute the A plus 190 in for B in the second equation. So I would get A plus 190 equals 1,510. So we get 2a plus 190 equals 1510. And then what we want to do is we want to subtract 190 from both sides. So subtract 190. So we have 2a is equal to 1320. And then divide by 2. So that gives us building A's height. So building A is, let's see, that should be 660. So that's building A. And then plug that in to get B. So 660 plus 190 gives building B. And so that's going to be 850 feet. That's the height of building B. And you can check, add them together, those do come out to 110. So again, not so much different from the first one, but we do actually have some sort of application. But they get a little more interesting with things like number 3, where we have Christine going shopping, and she's buying each of her 6 nephews a gift, either a video costing $14.95 or a CD costing $16.88. So here, let's say let's actually define our variables. Let x be the number of videos purchased, and y the number of CDs purchased. So defining our variables like that makes everything very clear. So we know reading the first sentence, or the first clause of the first sentence, she went shopping and bought each of her 6 nephews a gift. So she bought 6 total gifts. So that gives us an equation, x plus y equals 6. Then the second equation is going to be a cost equation. You know how much each gift costs, and then you know the total cost. So if you take the $14.95 it costs to buy a video and multiply it by x, and you take the $16.88 it costs to buy a CD and multiply that by y, you would get the total cost of $97.42. So this is our second equation. Again, I think substitution is the way to go here. Right, you can take the first equation and say, okay, this is x is just 6 minus y. So we can get our $14.95 and then change the x to 6 minus y. And then we still have our $16.88. Y equals 97.42. And what we want to do is distribute. So we do 14.95 times 6, and we get 89.7 minus 14.95y plus 16.88y. This will equal 97.42. So then what we want to do is we want to subtract the 89.7 from both sides to move my regular numbers to the right-hand side of the equation. And then combine our y's. So 1688y minus 1495y comes out to 1.93. So we end up with 1.93y equals 7.72. So when we divide by 1.93, we get that y is equal to 4. So she's buying 4 CDs. So 4 CDs, and we know the total 6, so that means x is going to be equal to 2. So she buys 2 videos and 4 CDs. And that's it for number 3 there. So a little bit of a trickier setup because you have a total number equation and then you have a cost equation. You find this thing in dilution problems too in chemistry a lot. A lot of times you have a total volume and then you have a volume of some part of the solution, whether it be salt or something else like that. So this next one's kind of a mixture problem because basically we're trying to make a trail mix by combining nuts and raisins. So let's just let N be the number of pounds of nuts and R be the number of pounds of raisins. Right, we have 2 things going on here. We know the total volume. So if you look at this one, we've got the cost of the nuts is 18 per pound, cost of the raisins is 6 per pound. And we're trying to make 60 total pounds of trail mix selling at $10 per pound. So this is going to be similar to the last question. We've basically got a total volume equation, and then we've got a cost equation. So whenever you have those costs, you're going to have to multiply them by your number of pounds to get the cost contributed from each component. So the total volume is the easier equation, right? We're making 60 pounds of this mix, so we know N plus R is 60. And then we want to do the actual total cost. So we know 18 times N plus 6 times R. This is going to give our total cost of $10 per pound times the 60 pounds, right? So I have to do 10 times 60, so that really gives me 600. So that's where I'm going to get the 600 from. And again, we have a pretty easy substitution. Let's say N is equal to 60 minus R. So we can go ahead and plug that in. So let me just do that right here. Let's say we have 18 times 60 minus R, replacing the N via substitution, and then plus 6 times R. This equals our total of 600. So what we want to do is we want to just multiply that 18 through. and we get 1080 minus 18R plus 6R equals 600. So again, we want to move the numbers to the right, so I'm going to subtract 1080. So I'm left with negative 18R plus 6R is minus 12R, and I'll be left with minus 480 on the right-hand side. So I divide by negative 12, and I get R equals 40. So I've got 40 pounds of raisins, which will leave me with 20 pounds of nuts. So N plus 40 equals 60, so N is equal to 20 pounds. Just plugging back into that original top equation. So it's important to note that does that answer make sense? When we have word problems, it's always something we want to try and think about. And notice if we used an equal amount of nuts and raisins, our cost should be right in the middle. And the cost of the nuts was 18 and the cost of the raisins was 6. So if you average those together, that would be an average cost of 12. So that means, at least in principle, we should be expecting to use more raisins than nuts. So an answer that's reasonable would be 40 pounds and 20 pounds here, right? So we don't see anything. If we ended up getting like raisins being 20 pounds and nuts being 40 pounds, then that wouldn't make sense, because we know that if they were 30 pounds and 30 pounds, we would get an average cost of $12, but we have an average cost of $10. Okay, so let's move on to the last one. So we have one of those infamous train problems, but it's really not so bad. As long as you set it up properly. Like I said, once you set up all of these, we just get a system of equations. So we have two trains starting from 385 miles apart. They pass each other 5.5 hours later. If one train travels 10 miles an hour faster than the other, find the rate of each train. So basically, I like to set these up using a distance equals rate times time chart, right? You probably remember that from grade school or high school. But distance equals rate times time comes up in these word problems all the time. So the thing we want to do is let's let x be the rate of the slower train. I just like to do that because then we know the faster train is going to be x plus 10. So it's really easy to set up. So let's see. Let's say we have train 1, train 2. So we would have the distance that each one of those travels. We would have the time it took them to travel. And then we would have the rate of travel. Distance equals rate times time. So maybe I did that in a funky order. So maybe I should do rate. Let's do rate and time on the left. I mean, you could do it in any order, but if we have rate and time, then we multiply them together, we get the distance. So let's try the chart this way. And the first thing we can fill in is the rate. That's how we defined our variable. So we know, let's call train 1 the slower train. It's going at x. So train 2 is going at x plus 10. So then what do we know? We know that the times, the total times is, so then we could even do like a total if we want a total column below. So let's say total, because we know two totals. We know that the total time, oh, no. So each one is traveling for 5.5 hours, so we don't have to worry about the total. So that's, I don't think we necessarily need that. But yeah, so each train is actually traveling for 5.5 hours, right? So basically what's happening is one of the trains is going to travel a little bit farther than the other one because they both travel the same time, but one's traveling faster than the other. And we know the distances. We get the distance by multiplying, right? Because distance is equal to rate times time. So x times 5.5 is 5.5x. And we get x plus 10 times 5.5 for the other one, or 5.5x plus 55. Okay, and then we do know that the total distance is, oh no, what do they want us to find? They want us to find the rate of each train. So if you add the two distances together that they travel, you should get 385 total miles, right? Because they start from 385 miles apart. Yeah, and then, I don't know, we could use different colors here. We could say train 1, it was traveling a bit slower. It traveled this far. Right, and then train 2, it was the faster train. It traveled this far. But after 5.5 hours, they pass each other on parallel tracks. And so we know that the total distance is 385. And we know the distance each one traveled. So if we add distance from train 1 plus distance from train 2, we should get 385. So we know 5.5. So yeah, maybe we can even label these, if that makes sense. 5.5x for the blue segment, and for the red segment, it's 5.5x plus 55. So that's what gives us our equation. So we get 5.5x plus 5.5x plus 55. This is equal to the 385 total distance. So we end up with 11x plus 55 equals 385. And then you want to subtract 55. So we have 11x equals 330. Divide by 11. We get x is 30 miles per hour. So that's the speed of train 1. So train 2 is x plus 10, which will be 40 miles per hour. 10 faster than train 1. And yes, for ones like these, when you have a formula, a lot of times it's really useful to organize your information in a chart, and then once you're done with that, you can write an equation kind of easily. Pictures are also helpful. We kind of combined it with the picture here to understand the segment each train was traveling, and that they combined for a total distance of 385 miles. But anyway, that's it for applications. Like I said, the tools are no different for solving the equations. It's all about just setting them up. So this is Dr. Lennon signing off.